Welcome to this third screencast of Module 8, which is on stack design. Now we will make the step from single cells to stacks. So you might wonder, why do I need a stack? Why can I not just use a very large single cell, tens or hundreds of square meters large? But in practice that's just not very practical. Because it means because an electrochemical cell is quite thin, it's typically only 1 to 10 centimeters thick or so, and then make something of 100 square meters, that's just not very practical, and also, for example, from a heat management perspective, it's difficult. And that's why in electrochemistry it's typical to make stacks, and you see one depicted here, and schematically you see one here. And a stack is basically just a number of cells put in series behind each other. And here you see a small example with four cells, but the number of cells can be significantly larger, can be 300 or even larger. The maximum cell sizes, so the square meters, is typically a couple of square meters. Larger, as said, is difficult, and one of the main reasons is heat management. So you might think that electrochemical reactors, electrochemical stacks are unique. They are, but they still bear resemblance to some other processes we use in chemical engineering. For example, heat exchangers or filter presses. Here, for example, you see a picture of a heat exchanger on the left, and here you see a picture of an electrochemical stack on the right. And you can see there are quite some resemblances. Basically, what you can say is that both heat exchange and an electrochemical process is a 2D process. It needs a lot of area. And then for those type of processes, these stacks are just the best solution. A key question is how you connect the stack electrically. There are two possibilities. You can either do it in a monopolar way or in a bipolar way. Let's start with the monopolar. In the monopolar way, you connect every anode and cathode. For example, here you see the connection of the anodes, the positive electrodes, and every one of them is connected. At the same time, also the cathodes are all individually connected. And what is interesting to see here is that you see here we have one cell with the cathode and the anode, and on the other end you can still use the same anode also for the other cell. So it's the anode for this cell and it's the anode for that cell in the monopolar configuration. In a bipolar configuration, you have a different setup. You only make the connection at the end of the stack. For example, you start here with the cathode, and then you get to the first cell. So here there is the anode, and the other side of that anode then acts as a cathode again. And in this way you continue until you reach the other side of the stack. Now, what is now a difference between monopolar and bipolar? Here on the right, in the monopolar system, the potential you apply to the plus and the minus is exactly equal to the cell potential. But here in the bipolar configuration, the potential you apply is 5 times the cell potential, because 1, 2, 3, 4, and 5. That's the potential. Now the other question is, what is the current? The current in this system on the monopolar is higher than just the current of a single cell, because every current needs to flow through every cell. So the current in this system is actually 5 times higher than for a single cell. On the bipolar side, the current is equal to a single cell because every uh, every electron that goes in here crosses through 5 individual cells. So the current is still the same as for a single cell. Then in total that means that the power is the same in both systems. Here the potential is lower, the current is higher. Here the potential is higher, but the current is lower. Here is a bit more in-depth information on the bipolar connection. As I said on the previous slide, in a bipolar system, an electrode can act both as a cathode and as an anode. Let's explain that a bit further by this picture. So let's say we have on the first electrode, we apply a potential of 10 volts with regards to the last electrode. So we start here at 10 volts, then we have our first cell, let's say it's 2 volts, which means that this electrode is at 10 volts and then the second electrode is at 8 volts. Now this 8 is significantly lower than that 10, so that's why this electrode acts as the cathode on this side. On the second cell, you start here at 8 volts and you have another 2 volts. You go to 6 volts. Now in this case, the 8 volts is significantly higher than the 6 volts, which means that this electrode now starts acting as the anode and the other one as the cathode. What you can say is that the potential difference over the electrode is very small because it's a metal. So it is actually 8 volts on both sides. It could be 0.01 volt difference, but a very small number. And so you can continue. This was 10, 8, 6, 4, 2, 0, and you continuously have these steps of 2 volts. And this forms the total stack. Okay, now let's see if you can see the differences between a monopolar and a bipolar stack. And for that, there's quiz question 8.5. Now, after all this explanation of monopolar and bipolar, you might wonder which one is better. For that, let's look at the advantages and disadvantages of both systems. Let's start with the bipolar. The bipolar has the advantage that you only need to connect it on two sides, so you don't need a lot of individual connections. So that's a disadvantage for the monopolar, where you need to connect every single electrode. The bipolar also has as advantage that you have a high voltage over the stack and a relatively low current. Whereas in the monopolar system you have a low voltage and a higher current. Now why is that better for bipolar? Because for the electrotechnical system, so the transformers and the rectifiers, it's cheaper to get high voltage and low current compared to low voltage and high current. Then another advantage of the bipolar system is that it's easier to achieve a good current distribution over the cell. And what do I mean with that? It means that the current here at the edges is the same as in the middle and is the same as on the sides. And why is that sometimes a challenge for the monopolar system? Because when you connect it on one side, there can be a bit of potential drop over the electrode. So for example, if the potential is 8 volts here, it could be 7.95 volts on the other side. And as a result of that potential being a bit lower there, you can get a lower current density at this position, for example, compared to that one. And that in turn could lead to faster electrode degradation. Now, last advantage of the monopolar system is that you don't have any bypass currents, whereas you do have these bypass currents or shunt currents for the bipolar system. Now, it's a bit difficult to explain what they exactly are, but it boils down to the fact that it means that a current can literally bypass the electrodes. And the current finds route to, for example, the inlet device, because all the cells are typically fed from a certain inlet device. And it's possible that the current decides, well, instead of going to the cells, I can also go through the inlet device. And if that happens, you lose the efficiency of the stack. So that's not good. There is an exercise on this, so that gives you a bit of a better feeling on yeah, what the shunt currents or bypass currents really are. But that's a disadvantage of the bipolar system. Now, yeah, now still the question, which one is more attractive? I think you can generally say that a bipolar system is more attractive from yeah, these three advantages. However, it's not always easy to use, or this fourth disadvantage can be too negative that you're forced to use a monopolar system. And therefore, you see both bipolar and monopolar systems being applied in industry with, I think, more recently the focus really drives towards bipolar systems. Well, that already brings us to the end of this screencast, so thank you for your attention.